Agriculture and climate are inextricably connected. According to Jeff Seal, the Director of Climate Policy and Strategy at Bayer Crop Science, agriculture is the number two contributor to atmospheric greenhouse gases. The sources of those emissions include, but are not limited to, the use of fossil fuels generated by the use of heavy equipment that is involved at every stage of the process from farm to table. The good news, according to Seal, is that agriculture can also be a part of the solution. Essentially, it boils down to the things we can do on the farm to remove CO2 from the atmosphere and store it in the soil. The soil, he says, has the potential to be the second largest carbon sink on the planet behind the ocean. Seal goes on to ask out loud, how do we leverage that? So central to the answer is an understanding of the relationship between growing organisms and carbon in the photosynthetic process. All plants, grasses, trees, fruits, and vegetables utilize carbon as the cornerstone of their structure. The enzyme rubisco separates carbon from oxygen and keeps the carbon as a building block of the plant and returns the oxygen to the atmosphere. Seal says the question is, how can we more effectively drive more of that carbon below the ground, as well as once it's there, how do we keep it there? And he says one of the exciting aspects of his work is determining how to work with microbial species that exist in the soil below the ground. He goes on to say, our aim is to embed that relationship into the seed and create the opportunity for that microbial species to grow right along with the plant root, and in doing so, set up a beneficial relationship, a relationship that will improve soil health, improve water retention, and increase yields. Jennifer Powers, a professor at the University of Minnesota, agrees. You really want to stuff carbon into a pool that has long-term storage potential, she says. That's because carbon in soil builds up over millennia. Once there, it can stabilize and become protected physically and chemically, building a long-term carbon pool. I invited agricultural climate specialist Dr. Jeff Seal to join me for a conversation that matters, food for thought episode about working with plants to help address carbon in the atmosphere. Jeff Seal, welcome to this episode of Conversations That Matter, Food for Thought. A lot of people are looking at agriculture these days and saying, you are a significant, if not one of the major contributors to greenhouse gases, namely carbon. And in your case, you're also studying nitrous oxide. And they're saying we have to do something about this. Are they correct in their assertion that farming is a major contributor to greenhouse gases? And if they are, then what is it that you are doing to help us to address this?
So first of all, thanks for having us today. It's really a pleasure to be here and talk about this work. And the answer to the question is yes. Agriculture is the second largest contributor to greenhouse gas emissions, and so it is a significant part of the problem. But the good news is that agriculture can also be part of the solution, and that's been the focus of the work that we've done. And essentially, it boils down to what are things that we can do on the farm to remove that CO2 from the atmosphere and store it in the soil. And the soil has the potential to be the second largest sink on the planet behind the oceans. And so the question then becomes is, how do we leverage that ability to make some positive impact?
So I already thought that agriculture played a significant role in the capture of carbon because of the process of photosynthesis, the role of rubisco or rubisco as you pronounce it. It's sucking or it's separating the oxygen from the carbon and keeping it in the plant. Plants have root systems, they're sequestering that carbon. Are they not? Is agriculture not already playing a significant role? Um, And if I'm correct there, then what can we do then to enhance that ability of agriculture to capture more carbon?
Right. So that's essentially sort of the biological chemical basis. Converting that CO2 into sugars that become parts of the plant structure. And the question becomes is how much of that sort of becomes more or less permanently removed, right? So everything above ground, things that we end up eating, that's sort of just a natural cycle, right? So,
Mm-hmm.
converted and then converted back to CO2 through sort of normal metabolic processes. But the question then becomes is, how can we more efficiently drive some of that carbon below ground as well? And then once it's there, how do we keep it there? That's another piece, right? So,
Mm.
a lot of agriculture involves sort of in sort of conventional ways have been how do we disturb the soil to do other things that are needed, right? To prevent weeds and those types of things. And so the question becomes is, you know, what are ways that we can put more carbon in the soil and then keep it there?
Mm-hmm. Because when we consume it and then we release carbon back out, that's all part of the flow. That's not necessarily the production of new carbon, but as you point out, it's not sequestering it. So then
Right.
the big question is how do you then get it into the root system and make sure that it stays sequestered within the earth? What's the path to doing that?
One of the things that's sort of exciting and new in this space is how do we work with microbial species that exist in the soil that may like form these relationships with the plant below ground. And we've worked on different microbial species and how do we create those in the forms of seed treatment, right? So you can apply that microbe directly to that seed, make sure that it's stable and viable. And then once you plant that seed, create the opportunity for that microbe then to grow right along with those plant roots. And so to set up this sort of beneficial relationship, right? And what we see is there are some microbes that actually provide more nutrients, more better uptake of nutrients to the plant, and so that creates the opportunity to create more roots, deeper roots, and so you get more carbon below the soil. But it's also beneficial to the plant, and like they get better uptake of nutrients, and so that's just one of the ways, and one of the sort of exciting ways that I think that a lot of people are looking at in terms of how do we use systems like that. And this sort of side benefit, and especially in the greenhouse gas piece, is like if you can get better uptake of nutrients, then you have to apply less of them, right? And so when you think about nitrous oxide, the better or efficient use of fertilizer, then you have to apply less. And so once you apply less, then you have less breakdown and less escape into the atmosphere. And so it's a overall greenhouse gas benefit, just not a carbon benefit, right?
Where are you at in this? Because it sounds quite exciting, and I sometimes have an opportunity to go, "Oh my gosh, this is really quite an interesting potential solution." Where are you in the development of this? Uh, is it still at the hypothesis stage, or are you already producing?
No, there are products that are currently sort of at the late stage of the pipeline and starting to be introduced as well. And again, we're not the only ones that have worked on this. And the idea is not particularly new in the sense that there are companies that have sort of sold these microbes as things that you can just add directly to the soil. But I think sort of the leap forward in innovation was really how do you apply that microbe directly on that seed and keep it so that it's stable and that it's viable. And so then when the seed is germinates, it's right there ready to go, right? Instead of just dumping it in the row itself.
Okay, and are you focused in on specific seeds at this time?
Primarily, we focus on corn and soybean because that's a big part of our business. But there's no reason to think that, that this technology isn't more widely applicable to crops in general.
Hmm. So, what else can be done from an agricultural perspective to uh, improve the environmental and especially atmospheric gases relationship between agriculture and climate?
So I think the sort of place of most focus that currently is because it's the simplest is really around agronomic practices, right? So how do we do things just on how we farm? So, tillage, for instance, right? So if the carbon is in the soil, we want to make sure it stays there. So, whatever minimal disturbance you can do. So really trying to drive the adoption of low tillage practices is one of the biggest impacts you can have, based on all of the modeling and the experimental work. And then the other is really around the concept of planting cover crops when that soil is, bare, typically bare in between growing seasons, and it has multiple benefits. One is it just adds more biomass to the soil, right? So you plant mass grow, you get more stuff underground as well. But then there are the side benefits of preventing nutrient runoff, preventing soil erosion, those types of things. So one of the nice parts about thinking about just greenhouse gases in agriculture is a lot of these things have these co-benefits as well. And so, not only are you working on the greenhouse gas problem, but, things like improving soil health, right? So adding these things to the soil is a carbon, and you get soils that are better able to retain moisture. And so then, whenever the growing season comes and the temperatures get really warm, the plants become more resilient. So it has an adaptation piece as well as this sort of mitigation piece.
So when you do this kind of work and you're dealing, let's say, with corn, how many different varieties of these microbial changes do you have to make? Because the corn that we plant in northern Saskatchewan is different than the corn that you're going to plant in Missouri or Texas or wherever. So how complex is it and difficult for you to ensure that you can now start to deliver this kind of solution to farmers throughout North America and maybe potentially around the world, because the growing conditions, growing seasons, the environments all must play a role.
Yeah, and so the way you deal with that is really just having a broad testing network, right? So how do you test? Because that's typically just part of the normal testing anyway, right? We test at different geographies, different environments. Because you're right, we have hybrids that are really good at parts of North America, and then different hybrids, and so the idea is once we identify technology, I think that we want to go forward with, then we try to test it as broadly across all of that germplasm as possible.
So I was talking to one farmer who I said, okay, well, then how do you know which seed to pick? And he said, well, the great thing about companies such as yours is that you will send people out to their farms and work with them to ensure that they have the right seed for their growing conditions. Is that part of the whole process of being able to deliver this?
Yeah, I think that having people right there in the field working directly with the farmers, and I think the other piece of that, and this is sort of like developing innovations, is really around the digital platform, right? So how can you take data and information directly from the farmers' fields and then apply that to your knowledge of your different seed varieties, and like how do you do the best match? And then we're able to test like seed spacing, right? Plant spacing. And so how do you like optimize that plant spacing? So that's all now been enabled by our ability to just take in massive amounts of data and analyze that, and collect that data real time. So now uh, with tools and iPads on tractors and connected directly to the cloud, right? As they harvest that yield monitor in that tractor can like upload that instantaneous yield information, and so you can compare directly. This
Wow.
spacing, all of the inputs that I put in this part of the field compared to that part of the field. It's like instant feedback on experiments, right? And so the cool thing about that is like now farmers across the US are able to do their own experiments. It's not just ours, right? So they know their field better than anyone, and so they can help. Okay, I want to this part of the field, I want to try these conditions, and then, different conditions in another. And they can sort of right there do their own experiments, which is, I mean, when you come to think of it, it's kind of a cool concept that we're turning all
Right.
these farmers to like real data-driven experimentalists. It's
Well, as I'm listening to you explain this, I realize that you're able to start to come up with a designer solutions for specific farms because you have this ongoing relationship, data relationship with the farmer, and you get to collect all this data as the plant is growing through to harvest, and then you say, okay, here's what we've learned about this specific area, and how we can enhance the quality of that plant to be as robust and productive as possible.
Yeah, I think one of the things that I mean, I didn't grow up on a farm, and so this is all not sort of natural to me. But one of the things I've learned over the last few years that I didn't have any idea was really, you think of a farm and you just think of a field and like, well, it's all the same. When in fact, it's not, right? I mean, the soil types can vary greatly across that field, and how the water drains and all of these things come into play, and they impact your ability to drive yield in different parts of the field, right? And so the coolest part about sort of this whole concept of these digital experiments is that, and the way the tractors are just so, and the planters are complicated these days, is like you can go along and know, okay, in this part of the field I need this planting density, but the minute I shift into this other part of the field, if I want to get the highest return, then the density has to change, and that all can happen automatically. It's like, just it just blew my
Yeah.
mind when it's like, wow, it's like it. And so when we think about soil carbon, it's sort of the same idea, right? It's like some parts of the field can capture more carbon than others just because of the nature of the soil types. And so how do we really do those analyses in such a way that we figure out how to maximize the ability to capture carbon on that field?
So when you do this kind of work and you're enhancing the ability of the plant to capture and sequester carbon, that is one side of the equation of addressing agriculture's environmental footprint. By doing this, do we also then also start to address agriculture's output, or is that a completely different strategy?
So I think we have to figure out how to do them in harmony, right? And so
Yeah.
that's sort of, I mean, when you go back to the original question here, right, is agriculture, part of the solution or part of the problem? And, in fact, the primary goal of agriculture is to feed what will soon be 10 billion people on this planet, right? So that
Yes.
comes with a cost, an environmental cost. And so, the real goal is how do I minimize that environmental cost while I maximize my ability to provide enough food for people? And so I think as you think about this, it's always like the balance that you have to figure here, right?
Well, we're not going to stop growing food to feed people because it is an essential element of life. But I can see that by what you're doing, if you're saying everything that we're doing to make farming more efficient and effective, and thus increase yields, will mean that we'll be able to produce more food without expanding the environmental footprint that we have now. Um,
That Yeah, that's exactly right. In terms of, so when we think about the total sort of contribution from agriculture to greenhouse gas emissions, sort of the biggest segment of that is the land use, right? And so, you know, the way that we can sort of have the biggest impact on the overall carbon footprint of agriculture is to maximize our ability to produce as much food as we can on as small a footprint as possible. And so if we wrap our heads around the idea that we can actually produce enough food now on less land, that land can then be returned to native ecosystem habitats that can sequester more carbon, right? And so that the ability to sort of sustainably intensify our food production on a smaller footprint enables us to take land out of production and return it to native habitats, which then has that added benefit as well.
Is it really possible for us to be able to do that, to produce more food on a lower land footprint? Or is
So
that
we've
what we
actually
hope
looked
for?
so we've actually looked into that, and it's like thinking about sort of modeling out over the next, couple of decades, how would that work, and is it possible, and what kinds of technologies enable that, and sort of looking at the rate of innovation and yield increases over time, and the answer to your question is yes, it is possible. The question then becomes is will we do it, right? And what's the right way to do that? And I don't think we have the answer to that question yet, but it definitely involves continuing sort of on this innovation pathway, and then combine that with sort of these other practices. These agronomic practices are going to be critical to that as well,
Hmm.
especially when we take into account climate change, right? Because part of that innovation and to get that to drive that yield such that we can reduce land, we have to do it in the context of adaptation as well, right? We have to
Well,
be able to make sure that we can continue to grow food in the places that we do, so that we don't have to take other places and put them into production.
well, you posed the question in your answer saying, "Will we do this?" Why wouldn't we do it?
I mean, I think the answer is we have to do it, right?
Yeah.
But there are, I mean, it's the current debate around what are sustainable production, methods, right? So sort of how we do it in North America. So people think that isn't sustainable, degrading land and all those kinds of issues, and push towards more regenerative, uh, practices, which have some benefits, but there are questions about the ability to produce a sufficient amount of food in some of those other systems. And so
Hmm.
I think that the question becomes is like, how do you create a system that does provide enough but also has those environmental benefits as well? And I think that where we sort of get into trouble is when we try to decide that, well, there's just one system.
Yes. Great. Well, thank you very much.